Now, sometimes you'll have tables that have 3 columns, and that's because instead of it being just one reactant to a certain exponent, you might have 2. You could even have 3. You can figure out the rate laws for these, but you have to pick the correct experiments. And I kind of make this similar to if you've ever gone to the doctor for some kind of a longer term condition and there's a lot of medicine possibilities. A lot of times what they'll be like is they'll say, oh, well, we're going to add on this medicine and then in 2 weeks we'll add on the next one. And the reason they're doing that is because they don't want to change 2 meds at the same time, because if you improve, you don't know which one has been changed that you've improved by. And that's also what we do for experiments. We've got to know which ones that we change and which ones we don't. We have to hold something constant in a lot of cases. So in this experiment 1 and this experiment 2, notice that the B is held constant. Not held constant, but it just means that when we put it in, we put in 2 molarity at both times. So it's effectively like saying we aren't changing when we're changing between those experiments. So this is the one that this would be a set of experiments that we would use well to calculate A, because B isn't changing. So if B isn't changing, you're not going to be able to calculate this one's value. I'll show you mathematically why in a second. In contrast, if you want to figure out B's, you need to find 2 experiments where A has not changed. And so like right here, you can see A hasn't changed in those ones. So when I figure out this, it's kind of like I'm going to do this twice, and I'm going to do it twice with different experiments. So one set of experiments I'm going to use is this set, and I'm going to use it with the A. And then the other set of experiments that I'm going to use is this set, and I'm going to use it with the B. As a note, I could have picked other experiments for A, because notice, like here, those 2 both are held constant there too. Or, I mean, I didn't have to pick those ones to figure out A's exponents, but I do have to pick these 2 for B, because these are the only sets where A is held constant. So the key on this is picking the right experiment. Now, if you remember the generic format we were saying, or I was saying that you would use to calculate one of these would be rate equals one of these over each other, copy. And then remember that the K will cancel out. And then remember that you can rewrite your A's and your B's as being raised to the, just one second. You can write your A's and your B's as being with parentheses around them. So I have A over A. That'd be like 2 and 1 to the M. And then I can do B, 2 and 1 raised to the N. And so that's the generic format. But because of how I'm going to put these in, remember, I'm putting in this one and this one. So I just want to show you, if I do this and I do put those ones in, and I will go back and fill in the other amounts too. But I want to show you what happens. So if I put in 2 and 2 in both those cases, so 2.0 and 2.0, then that's the same thing as saying this is 1 to the N. And it doesn't matter what N is, 1 to the anything is always 1. So it's like multiplying this whole bit times 1, which is why we need to pick these experiments, because we want to get rid of one of these 2 variables. I have one equation right here, and I have 2 variables, and I don't want that. We need just one thing to change, just like the doctor would do. So this is great. This means that this term is going to go away, and that leaves us with what we really wanted anyways, which was the rate 2 over rate 1 equals A2 over A1 to the M. That's just the same format as before, and so these are actually the same numbers as before. So if I were to move this over, that would make that to the third, and that would be 26. So we've actually already done these numbers before. So 26 times 10 to the minus third over 8.6 times 10 to the minus third, and the minus thirds cancel. And then A2 is 0.9 over 0.3 to the M. So that tells us we have 3 times 3 to the M. And so when we zoom in, we can say that that's the same thing as saying that M is 1. So we have A's rate law, but we don't have the whole thing yet. If we look back up here, we know that A is to the 1, but B is still unknown. So we're going to do the same process, and the same thing will happen when we pick on this step between here and here. If I pick a scenario where A is the same, so copy, bring that over here, bring these over to the left a little bit. So like in experiments 3 and 4, let me double check which one I want to be bigger. So yeah, if I move this over, that will make this 1 times 10 to the 3rd. So I'll make it 11.5. So I want 4 to be on top. So if I do that, then I'll have 0.1 over 0.1 to the m. But again, that's the same thing as saying 1 to the m. And so that m term goes away, which is great. And we're left with the rate 2 over rate 1, except I want that to be 4 and 3, don't I? Rate 4, rate 3, rate 4, rate 3 equals just my b term. And again, that's still 4 and 3. So now when I put those in, I have 11.5 times 10 to the minus 3rd, and I have 2.8 times 10 to the minus 3rd over, and then b4 is 2, and then this one is 1, and that's raised to the n. So if I zoom in on that and I pull over my calculator, I have 11.5 divided by 2.8, because remember my times 10 to this cancel out. So that's left with 4, and then this is 2 to the n. And to solve this, I either bring the n to the front and take the log of both sides. Like I take the log of both sides and that brings the n to the front. Or I just need to make sure that these have the same base. So this needs to be base 2. And then I can see that n is equal to 2. I can also do these by inspection as a little note. So my rate law for this one would become that to the 2. If I am doing this by inspection, just make sure that you are still picking the correct experiments. I still need to pick like a set of experiments like this. Well, I like going the other way. So I still need a set of experiments like this. That's times 3. And then this is a factor of 3. So that makes this one first order. But then I have to pick these ones, and that's times 2. This is times 4. So I can tell that's not first order. It's got to be second order.